Okay, so in this lecture, we'll continue our discussion on the multivariate normal. So here is the multivariate normal random variables, which we write that follow a normal distribution with dimension n, with mean mu and the covariance matrix sigma. So here the random variable y is a n by 1 vector. The mean mu it's also a n by 1 column vector, and the covariance matrix is a n by n matrix, and also is symmetric, meaning that sigma transpose is equal to sigma. Okay, and then we also have the following density function for this random variable y, which is 2 pi raised to the power of the dimension, which is n here over 2. And then we have the determinant of the covariance matrix, and then raised to the power of 1 over 2, and then multiply by the exponential for of negative 1/2, and then y minus mu transpose. So that will make it a row vector, and then sigma inverse, and then y minus mu, and then closing that. Okay, so this is a row vector multiplied by matrix multiplied by column vector. You will have a scalar in the end, and then everything here is also scalar. Okay, so we talk about that regarding the density function, and we also provided the momentary function. So m of y, which and a function of t, is equal to the exponential of t transpose mu plus 1/2 t transpose sigma t. So this is the momentary function for a multivariate normal distribution. Okay, and then on Tuesday we talk about two results. So that is a linear transformation ay plus c is also following a normal distribution with the mean is equal to a multiplied by the mu from y, and then plus c, and then the covariance matrix is a multiplied by sigma multiplied by a transpose. And then on Tuesday, this is the result that we derive. And we also have the following result. So you can call this result 1, and we also have another result, which is ay is independent of by if a sigma b transpose is equal to 0, a zero matrix here. So this is the true result. And in today's lecture, I'm first going to make some comments regarding the covariance matrix, or specifically the spectral decomposition of the sigma matrix, which is a n by n matrix and also symmetric matrix. Okay, so for a symmetric matrix, you can always perform this spectral decomposition and then write it as a matrix P multiplied by a matrix lambda and then another matrix P transpose. So here this P, which is defined or it is constructed as the eigenvector E1, E2, and then all the way to En. And then these are the normalized eigenvector. So I will comment a little bit later. And then the lambda matrix is a diagonal matrix where the 1, 1 entry is the eigenvalue corresponding to this eigenvector for this matrix sigma. And then you have the 2, 2 entry, which is the second or the eigenvalue corresponding to this eigenvector, and then all the way to sigma n. And then for the rest of the location, the entries, they are all going to be 0. So this is just a matrix, a diagonal matrix, with the diagonal having the eigenvalue of the covariance matrix sigma. And then if you place all these components, for example, the eigenvector, the normalized eigenvector on the column of P, eigenvalue on this diagonal matrix, and then you can decompose your covariance matrix into P multiplied by lambda multiplied by P. And here we're also going to make some comments regarding the normalized eigenvector. So the eigenvectors have the following properties, which is when you have the eigenvector taking the inner product with the other eigenvector for I equal to I, you will always equal to 1. So this is a n by 1 column vector, and then when you take the transpose, it becomes a row multiplied by another column vector. You will end up with a scalar. And then for I, well, here I already write it, for EI multiply inner product with itself, you have 1. And then for the eigenvector multiplied by another eigenvector for I not equal to j, you will get the 0. So that means if you multiply P and P transpose, so this is a n by n multiplied by another n by n, you will get a identity matrix. And if you have these properties, you can see that the P transpose is essentially equal to P inverse. So that you also have the following. So P transpose multiplied by P, because it will also give you the identity matrix. And the identity matrix is just referring a diagonal matrix with the main diagonal involving all the 1s, and then the rest are all 0s. So you will have the following property for this matrix P. Okay, so this spectral decomposition here are useful to calculating the power for this covariance matrix. So here are some of the results. So for example, if you want to calculate the inverse of this covariance n by n covariance matrix, this is equal to your matrix P multiplied by lambda inverse and then P transpose. And then the lambda inverse, since the lambda is just a diagonal matrix, you essentially just take the inverse for the elements in the main diagonal and then multiply by these the P matrix or the eigenvalue, the normalized eigenvectors. So let me put it here. Normalized eigenvector. Because after you're normalized, you will have these two. When EI multiplied by EI, you get 1. EI multiplied by EJ, for I not equal to J, you get 0. And then the reason you get 1 and 0 is because it's normalized. And then if you take the inverse for this diagonal matrix, you essentially just take the inverse of the main elements because the rest are just 0. And then that will give you a way to calculate the covariance matrix inverse. And then similarly, if you want to take the 1/2 power, this is equal to, you take the inverse and then take the square root for the main diagonal elements in the lambda matrix. And let's see. Let me also put it in. So without taking the inverse, this is equivalent to just taking the square root for the main diagonal elements. You will have that. Okay, and then you can construct lots of things from this from these 3 components. So for example, the original covariance matrix, it's equal to the covariance matrix 1/2 multiplied by that. And then if you use this particular notation, you will have P lambda inverse P transpose, and then P lambda 1/2 P transpose. So these two will give you an identity. So you have P lambda in 1/2 lambda 1/2 P transpose. And then here, because you just take the square root for this diagonal elements, and then you have another copy, sigma 1/2, you will end up with P multiplied by lambda matrix, and then P transpose. And that will give you the sigma matrix itself, the one that we decompose it in this way. Okay. And that is for the covariance matrix itself. And then the covariance matrix inverse can also be obtained by covariance matrix negative 1/2 multiplied by negative 1/2. And then if you plug in the component from here, this will be 1/2 P transpose, and then P negative 1/2 P transpose. And this again will give you identity matrix, and then you will have P lambda negative 1/2 negative 1/2 P transpose. And then for these two, because you are essentially just taking the inverse and then the square root, so 1 over square root of lambda, and then 1 over square root of lambda 2, and then there are only elements in the main diagonals. So if you take the product of these two matrices, it will give you P negative inverse, just 1 over lambda I, and then P transpose, and this will just return the covariance sigma raised to the power of 1/2, or the inverse of this covariance matrix. So here, when you use the spectral decomposition here, sometimes it can be very helpful to calculate some of the terms, such as the inverse of the covariance matrix, or negative 1/2 or 1/2 power for the covariance matrix. So here are some of the properties and result for using spectral decomposition on the covariance matrix. Okay. Now we can, once we have these kind of a result on constructing the 1/2 power for a covariance matrix, and then we can talk about some distribution of quadratic forms. And this is of normal random variables. And then we are particularly focusing on chi-square distribution. Okay. So here are also some of the results. So first, let Z1, Z2, and then let's say Zn following IID standard normal. So these are just scalar, like a real value. And then you can write Z as a column vector. So this is a n×1 column vector following a multivariate normal with 0 vector and then identity covariance matrix. So you just concatenate this in a column vector so that this is an n×1 and n×n, and then only the main diagonal are 1. And then here are the construction that we did earlier. When you have Zi for the scalar, taking the square, sum them all together, then they're independent. Or you can write it as the inner product. So 1/n multiplied by n/1. So these two operation or notation are essentially the same. And then this, as we mentioned earlier, will give you a chi-square distribution with degree of freedom n. So if you want to call this like a V, and then you construct it in this way, and then the V that you constructed will follow a chi-square distribution, degree of freedom n. And this is for the Z following standard normal distribution. And now let's make the Z more complicated and see how we can transfer different normal distribution into chi-square distribution. So for example, here we let Z again following a 0 mean. So let's also write this as a column vector, dimension n. But here, instead of identity covariance matrix, let's multiply by sigma square identity n. So this is so identity matrix is something like this. And then if you time a sigma square to that, you will just have sigma square on the main diagonal. Okay, so now if we write it in this way, so again I'm going to use the scalar version and the vector version to write it. So when you sum n copies, because you have zeros on the off diagonal part, so that means each of the elements in that Z columns are independent, so that you have Zi minus a 0 over sigma, and then all together taking the square. So Zi is not from standard normal, but if you minus the mean over the variance for the Zi, because each of them, they all have the covariance of sigma. So let me write it in this way. So Zi following IID normal and 0 sigma square. So this is the scalar version and this is just the vector version, but they are essentially the same. So if you minus the mean over the standard deviation and then together taking the square, this is essentially equal to this Z transpose Z, but divided by a scalar and then square. And then you will again obtain a chi-square distribution, degree of freedom n. So the difference is that here, this is more like a definition thing. When you square independent standard normal random variable and some n copy of them, you get a chi-square degree of freedom n. So here is that this is not standard normal anymore, but if you standardize it, that will become a standard normal. And then performing the square and the summation operation like this one, you again obtain a chi-square random variable degree of freedom n. And here just the matrix vector multiplication version notation for that. Okay. And then let's make it even complex. So let's write y following a normal dimension n. And then now no longer center around 0, but let's center around the mean mu. And then the same covariance matrix. This is still a diagonal matrix. And then you can write it as summation Zi. So maybe let me also write it the scalar version. So this is the vector version. And then for the scalar version, for each of the elements in this yi is also a normal with mu I from this column, and then covariance equal to sigma square. So that means you have yi minus mu I and then over sigma. So after you standardize it, taking the square, and here this mu is also equal to the scale. So although here's mu I, but the mu are essentially the same. So here this vector n minus 1 is equal to mu multiplied by a vector of 1. And then it will give you a vector of mu where the mu are all identical. So that means you don't need the I if you don't want, as the mu they are all the same across I. So if you have that, this is equivalent for y minus mu transpose y minus mu sigma square. And then you will obtain a chi-square random variable degree of freedom n. So again, you standardize it, taking the square, sum them together, and then this is the vector notation. You will still get the chi-square of n. Okay, so now we make it more general. In addition to only diagonal matrix, let's make it not diagonal. So you have the same, well, here you have the mean mu, but not necessarily they have to be all the same now. So that means mu I can be different from mu j by just a column vector, n by 1. And then you also have a covariance matrix sigma, so n by n. So this is not necessarily diagonal. So previously we have all these. But now you have the full covariance matrix, like sigma 1 2, sigma 2 1, all the way to sigma n squared, sigma n1, etc. So for this kind of matrix, you can also standardize it, and then taking the transformation. So here, let's define V is equal to sigma 1/2. So this is equal to this particular or related to this particular notation, and then multiply by the column vector minus that. So n by n multiplied by n by 1 minus n by 1, you will get the n by 1. So this is the matrix vector notation for the standardization, such as yi minus mu over sigma. And then this is not the square version yet, so this is just this part. You standardize it to standard normal. So this thing, if you want, right now is following a n-dimension 0 vector identity matrix. Okay, so to show this, you can calculate the expected value. So E of V is equal to sigma negative 1/2, because this is a constant, this is not a random variable. And then the random variable is referring to the random variable y, and then minus a mu. But y here is also having the expected value equal to mu, so you will have 0 minus 0, so that is 0 vector. Okay, and then for the variance of V, this is equal to the variance of a linear transformation. So sigma 1/2 for y minus mu. And we can use let's see, maybe I can write it more, and then variance of y minus a mu multiply by this one transpose. But because the sigma matrix symmetric, so sigma matrix raised to the power of negative 1/2 is also symmetric, so the transpose adjusts itself. Okay, but then with this one, this is a constant. So if you shift a random variable by constant, it's not going to change its variance, because the variance is just how the variation for this random variable. So if you just shift left and right for this random variable, it's not going to change the variance. So this is still going to be the variance of y. Okay, and then the variance of y is equal to the covariance matrix sigma. So you will have sigma 1/2 sigma sigma negative 1/2. And then they will all, or if you want, this is that multiplied by that, you will have an identity matrix. So you can see that now the V, or if you want, you can just use the result 1 that we have here. To see that a linear transformation of a normal random variable still going to follow a normal, and then it has the mean 0 and then identity covariance matrix. So this transformation will transfer a general normal random variable to a standard normal random variable. Okay, once we have the standard normal random variables, again, we can just take V transpose V. You will have y minus mu transpose sigma 1/2. This is for V transpose. After I take in the transpose, the order change. And then you have the sigma 1/2 y minus mu. Okay, and then if you combine these two together, y minus mu transpose sigma inverse y minus mu. And this will give you a chi-square distribution because the V is standard normal, and then this you can use the property 1 from here. If you take the standard normal transpose multiplied by standard normal random vector, you will get another chi-square. So in this section, we basically introduce from standard normal and the diagonal covariance matrix, and not center around 0, and then a more general form. And then they can all, after some transformation, to construct some chi-square random variables. Okay, so after we discuss the quadratic forms of normal random variables, and next I'm going to talk about another result. So if you want, you can call this a result 3. So let me write down. So let x1 and then to xn following so these are the scalar version. And then arbitrary mu and the sigma square. But they have the same covariance or the mean value here. And now let's define S squared equal to the summation from 1 to n xi minus x bar, taking the square, and then over n minus 1. So here note the difference. So we're not divided by n, we're divided by n minus 1. And then once we have this defined by we define S squared in this way, and then we have the following thing: n minus 1 multiplied by sigma square over multiplied by S squared, the one that we define here, divided by sigma square. This one follow a chi-square distribution, and then with degree of freedom n minus 1. So note the change here, the degree of freedom. Okay, and next we're going to prove this result here, and then also using some of the things that we get that we write down earlier. So the proof is the following. Okay, so first of all, let's start with the following expression. So summation from 1 to n. And then for xi, here, each of them, minus the mean mu over the sigma, the standard deviation. So after this transformation, you will have this one follow a standard norm of mean 0 and variance 1. And then if you take the square, sum them together, you will have the chi-square random variable here with degree of freedom n. So this thing follow a degree of freedom n. So here is n minus 1, this is n. So this is a known result, or that we also write down in 1 here. But we are going to show or to prove this quantity following chi-square degree of freedom n minus 1. Okay, so let's start with this known result and then perform some transformation. So here, let's start from this quantity. So summation 1 to n, let's write xi minus a mu, and then we plus minus x bar, and then over sigma taking the power of 2. So if we plus and minus, the same thing, we do not change any quantity here. So this thing should still follow chi-square degree of freedom n. Okay, so here let me also so the x bar is just the summation of xi over n. That is what the x bar is referring. Okay. And then let's group the things accordingly. So from 1 to n, xi minus x bar plus x bar minus mu divided by sigma taking the square. Okay, so right now this is still the same as we are just plus and minus x bar, so it's still following chi-square degree of freedom n, and then we're going to group the things in this way, and this will give us the summation from 1 to n, and then we're going to group xi minus x bar as one quantity and x bar minus mu as another quantity, and then we're going to expanding the square term. So we will have xi minus x bar square, and because the bottom, the denominator, this term here, is just a constant, so you can write it as here square root, or you can also write it as here sigma square. So it's just up to your preference. So I'm just going to bring the summation to the numerator, because this is just a coefficient, and then you can always move it to the to the front. Okay, and then the plus, and then summation 1 to n x bar minus mu square over sigma square, and then you will plus 2 multiply xi minus x bar multiplied by x bar minus mu over sigma square. So this is like the a square, b square, and then 2ab, and then the 2 is just a constant, so you can again move it outside as a coefficient. Okay, and next we're going to analyze the 3 terms here. So first of all, this term is going to stay the same, as there's no other ways to simplify further, so we're going to copy again. So xi minus x bar over sigma square. But this thing can be further simplified because x bar is just a constant. The mu is also a constant, so it's just a constant square, and then you have n copy of them. So that means you have n multiplied by x bar minus mu square over sigma square. So there's no more summation operation here because they are all just constant, so you have n copies of them. And then similarly, you will have 2 times x bar minus mu. This is a constant, and the summation index I only going to affect the terms that involving index. Okay, so that's one way to simplify it. And next, let's also look into the third term. So here I want to say that summation, because there's no okay, so I'm missing a square here. Okay, so because there's no square on the last term, so summation of xi minus x bar from 1 to n, this is equal to the summation of 1 to n xi minus summation of x bar. But x bar is a constant, so it just n multiplied by x bar. But x bar, okay, so let me write it in this way. So x bar is defined as summation of xi over n. So summation of xi is just n multiplied by x bar. And then this summation of x bar, because x bar is a constant, and then you have n copy of them, so you still having n multiplied by x bar, and that will give you a 0. So that means the third term will just becomes a 0. So that will give you the first 2 terms are remained. So summation I to n xi minus x bar square over sigma square, and then n multiplied by x bar minus mu over sigma square. Okay, so now I'm going to rewrite the second term in the following way. So I'm going to remove the n in the numerator and move it to the denominator. So you will have this divided by n. Okay, so if you divided and then divide another n, this is equivalent to multiply on the numerator. But I'm going to write it in this way, and then you'll notice that let me also write it here. Okay, that's that. And then I'm also going to write it, let's see. Oh, this is a plus. Okay. And you will have x bar minus mu over sigma divided by square root of n, and then together raised to the power 2. So I'm just going to bring, so the standard deviation divided by square root of n, and then I'm going to square the whole thing together. Okay, So now let's analyzing the first term, the second term here. So we know that xi, iid, normal mu sigma square, and then x bar is going to follow the same mu and then the sigma square over n. I think this is a result that we derived earlier as well. And then here, you can notice that we are standardized minus mu over sigma divided by n. So this is a standard normal. So I follow, okay, 0 and 1. So this thing is a chi-square. It's a chi-square random variable when you're taking the square. Degree of freedom 1, because you only have one copy of standard normal. You're taking the square and the degree of freedom 1. Okay. So we started with a terms with degree of freedom. It was a chi-square random variable, degree of freedom n. And then after we decompose it, one of the component is chi-square random variable 1. And then you can see that this one here, based on our definition for the S. So let me rewrite this one here. This is just the same thing as n minus 1 s squared divided by sigma squared, as the summation xi minus x bar squared is s squared multiplied by n minus 1. So that's why you have this one here. Okay, so this is the quantity that we want to show, or we want to check the distribution, whether it's following chi-square degree of freedom n minus 1 or not. We have the left-hand side equal to the chi-square degree of freedom n, and when we also have one copy of 1, degree of freedom 1. So now we need to check one more thing here, which is the independency. And then we're going to use that independency to get the distribution for this one. So now we are going to examine the following thing. So examine the independency of x bar and let me write x minus x bar. Okay, so these are the things that we need to check, and then later I'm going to relate the these two terms back to this expression. So let's first check the independency between this. So x bar just 1 over n summation xi, and this is just 1 over n with a vector of 1 multiplied by x. So this is a 1 by n row vector of the transpose n by 1. So this is the summation of xi divided by n. And then you have that, and then we are going to denote this as a multiplied by x. Okay, so you will have a vector multiplied by matrix vector x. Okay, now let's take a look at the x minus x bar. This is just x1 to xn minus x bar to x bar. Or you can write it as x bar multiplied by column vector of 1. So this is a scalar multiplied by a vector. Okay, and then you will have x here minus 1 over n for the x bar, 1 transpose x. So this is for the scalar, and then multiply by that. But here we are going to make some changes, as we're going to write this as a matrix multiplication. So I'm going to change the order as identity matrix dimension n, and then minus 1 over n 1 transpose. So this together multiplied by x, and this is a n by n, this is also a n by n. So n by 1 column vector multiplied by 1 by n row vector will give you a n by n matrix, and this is a n by 1. And I'm going to call this b multiplied by x. So we can write these two terms as a linear combination of normal random variables. And now using the result 2, so a sigma b transpose, and this sigma is the sigma for here. So that means the sigma is the lowercase sigma square multiplied by identity. And then let's examine a sigma b transpose. So a here is 1 over n 1 transpose, and then sigma matrix here for x is the sigma identity n, and then b transpose. So b is this one, and this matrix here is also symmetric. So b transpose is just b itself. So you have the identity n minus that. So this is a 1 by n row vector, n by n matrix, n by n. So you should have a 1 by n. And let's check if this is equal to 0 or not. So let's simplify that. We should have, let's bring the scalar outside. So 1 over n is a scalar. Sigma squared is a scalar. Identity multiplied by 1, you will have 1 transpose here. And then you also need the identity multiplied by this. So 1 over n is a scalar. And then vector of 1 from here multiplied by vector of 1 transpose. Okay, let's see. And then this one, these two things here, it's just equal to n, right? You have a row vector of 1 multiplied by column vector of 1. It's just n of 1 summed together. One minus 1 over n multiplied by n. So this is a column vector of 1 multiplied by column vector of 1. n multiplied by n, 1 over n is 1, multiplied by a vector of 1, that will give you 0. Therefore, x bar is independent of x minus x bar. Okay, once we have that result, let's circle back to here. So the x bar is referring to here, and the x minus x bar is part of the definition for s, because s square is a function of x minus x bar, because it's just x minus x bar transpose x minus x bar. So that means these two things are independent. So you have the following from the moment changing function. So if we define the first thing as q, and then okay, so let's define the first part as q, the one that we started with, and then we write as q1 plus q2 where we decompose into two terms. And we also know that the q1 and q2 are independent. So that means the moment changing function of q is equal to the moment changing function q1. Let me write t multiply by the moment changing function of q2. Okay, and this is because they are independent after we check that x bar is independent of x minus x bar. So what should I write? Okay, let me write then. So q is equal to the first term plus the second term, and then they are independent, so the moment function of q is equal to the product of these two. Okay, and then we know that the left hand side is a chi-square random variable degree freedom n. Okay, so let's write, so what we want is the moment generated function of q1 equal to the moment generated function of q over moment function of q2. And then we know that the chi-square random variable we have the n over 2. That's for the left hand side, because we started with chi-square random variable degree freedom n, and then we divided by another chi-square random variable, but with degree freedom 1. So this is 1 over 2, because the q2 is a chi-square random variable degree freedom 1. So that will give you 1 minus 2t for n minus 1 over 2. So this tells us q1, which is n minus 1 s square over sigma square following a chi-square random variable, because this is the formulation of chi-square random variable, chi-square moment changing function, degree freedom n minus 1 square. Okay, so that is the result that we prove here, the result 3. Okay. Next, let's talk about some other. Next, we will conclude the discussion or the lecture with a few examples that are related to the construction of chi-square. So here is an example. So let's add x1 all the way to x10 following a normal with mean 0 sigma square, and then find a constant c such that the probability of x bar over 9 multiplied by the sample variance for the x's less than c has the probability of 0.95. Okay, so the things that we need to do is that we need to construct a random variable that follow a distribution that we are familiar with, and then we can use the, let's say, the table or some like the distribution to find the p-value or the quantiles such that the probability under the curve has a 0.95. Okay, so in this formulation we have the x follow normal, so it kind of like x bar is related to some normal distribution, and then from result 3 we know that the x square is somehow related to the chi-square, so we are going to manipulate the terms here to make it chi-square over normal over a chi-square. That essentially will give us a t distribution. So we're going to manipulate in this way to get our distribution and to find the quantile c. Okay, so let's write down some result here. X bar following a normal 0 sigma square over n. This is already known, and we also know that the n minus 1 s square divided by sigma square here following chi-square random variable degree of freedom n minus 1. So we can construct the following. So x bar minus 0 over sigma square over n. Okay, so let me put it the square root here. So this thing should follow a standard normal now, and then let's divide it by n here. Okay, so let me also put in the number. So the n here are 10, and then the n minus 1 is 9 multiply by s square and then over the sigma square. So this is a chi-square distribution, degree of freedom 9, and then if you divide it by the degree of freedom 9 and taking the square root, so this will give you a t distribution, degree of freedom 9. So this is the construction that we have earlier. But now we need to draw the connection with this part here so that we can find the c under a t distribution. Okay, so let's simplify a little bit here. So I'm going to bring the 9, the square root of 9, from the denominator of the denominator to the numerator. So you have square root of 9 from here. And this is also the denominator of a denominator. So I'm going to bring it to the numerator. So we'll have square root of 10. Okay. And then the x bar minus 0, you just say x bar. And then in the two denominator here, we have the sigma square and sigma square. So they cancel out. And then we only left with the numerator. So 9s square root Okay, so so this is equal to that after the simplification. Okay, and now you can see its resemblance between these two terms, except that we are multiplied by a constant in the front. So that means, so this follow a t distribution. So now let's going back to the probability for the probability notation. You will have 9 maybe let me already group them together. 90 square root of 90 multiplied by x bar multiply by that, and then less than. So what you want is this term less than c, but here you multiply by square root of 90, so you also need to multiply by square root of 90 multiply by c. This one, you want the probability 0.95. So you have a t random variable degree of freedom 9 less than 90 square root of 90 multiplied by c. So now you need to find the quantile for square root of 90 multiplied by c. And under the t distribution degree of freedom 9, that should be 1.833. So you can double check using the table, and then the c, if you take the division, just 0.19. So make sure you check these two numbers. But the idea is just you construct a t random variable, you find a quantile. So I'm not sure if this number is correct or not, but you can just look it up and then take the division, and then you find a c. But the key idea here is that you need to construct a t random variable, and then to find the quantile, and then set this part equal to quantile, find the value of c from the original problem. Okay, let's do let's do one more example then. So x1 to x5 following standard, not standard, but mean 0 sigma square. Find constant c such that such that c multiply by x1 minus x2, and then x3 square plus x4 square plus x5 square following a t distribution. And then you can find a t distribution arbitrary degree of freedom to satisfy this, but the idea is to find a c. Okay, so x1 minus x2. So x1 and x2 are normal random variable, so x1 minus x2 is also going to follow normal. But the problem is, what is the mean and the variance? So e of x1 minus x2 is equal to e of x1 minus e of x2 0, because it's a 0 minus a 0. And then the variance of x1 minus x2, because they are independent, so it's just the variance of x1 plus the variance of x2, you will get 2 sigma squared. And then they are normal, so x1 minus x2 over square root of 2 sigma should follow a normal 0, 1. So we have some transformation on the numerator. Okay, now let's find about the well, here we already noticed that xi, so xi minus 0 over sigma, and then when you square them, or xi square over sigma square should follow a chi-square, degree of freedom 1. Okay, so that's another thing that we know. So that means we can write the left hand side in the following way. So xi minus x2 over square root of 2 sigma. So this is the numerator, and then divided by x3 square, x4 square, x5 square, divided by sigma square. And then here also divided by 3, because here each of them, including the coefficient here, that in the denominator that they share, it's a degree of freedom, chi-square degree of freedom 1. 3 copy of them is a degree of freedom 3. And then when you take the square root, so you have a normal divided by chi-square divided by its own degree of freedom. So this is a t distribution, degree of freedom 3. Okay, so now we just need to mimic the formulation for here, and then we find what is the constant c that we have multiplied here to make it t distribution, degree of freedom 3. So you can see that the square root of sigma and sigma here are cancelled out, and I'm going to bring the square root of 3 in the denominator of this denominator to the numerator. So that means we have that this is equal to square root of 3 over square root of 2, or let me write it 3 over 2. So this one to the numerator multiply x1 minus x2. Yeah, there's a square root, so x3 plus x4 plus x5. Okay, and this follow a t distribution. So comparing to this formulation, this will serve as your constant c. So if you multiply by this constant, and then also you divide it and divide it, which is just equivalent of multiplying by 1, and then you will find a t distribution, degree of freedom 3, and then the c, the constant part, has to be 3 over 2. So that will be your c. Okay, so I will pause here.